Hi, and welcome to my podcast for the collaboration on riverine ecology for the University of Wisconsin-La Crosse. My name is Robert, and I'm a math major. I've been partnered with a biology major for a research project this summer. Our research focuses on an invasive species within the Mississippi River ecosystem, Bithynia tentaculata. Bithynia are invasive snails and are originally from Europe. Bithynia can act as hosts for parasites such as Cyathecodile bushiensis, Sphydiotrema globulus, and Sphydiotrema pseudoglobulus. When infected snails are ingested by waterfowl, the parasites in turn kill the waterfowl, and they've been doing so in large numbers. Here's a very basic representation of the system. The cycle starts out with parasite eggs being released in waterfowl feces into the ecosystem, where they find their first intermediate host in Bithynia tentaculata. When the time comes for the parasite to move on to the next stage in its life cycle, the parasite sheds from the first intermediate host and finds a second intermediate host in either Bithynia tentaculata again, or in some native species like phisids. Once in the second intermediate host, the parasites are ready to be ingested by waterfowl, which are the definitive host in the system. It is here where the parasites reside in the digestive tract and can kill the waterfowl within only a few days. Parasites have been known to alter the behavior of the hosts in many species. Generally, this is done to help the parasites successfully complete their life cycle. We wanted to see whether or not this behavior change is present in the Bithynia Cyathecodile interaction, specifically when the Bithynia serve as the second intermediate host to the parasite. We hypothesized that the infected snails might move more or faster, or generally just with a different pattern than non-infected snails, to make themselves more visible to waterfowl, so they'll be more likely to be eaten and help the parasite complete its life cycle. To monitor the snail's movement, we set up behavior chambers where the snails are able to move around in. The snails are filmed for 3-hour increments with 20-minute acclimation periods to get used to the environment. The movement is filmed from above with either a video camera or just a regular camera. A ruler is in the shot for calibration, which we'll talk about later. As well as filming infected individuals, we also film controls to set a baseline for what normal movements are like. While filming the snail's movement, our cameras are connected to a program called Stop Motion Pro. The program takes a picture of the snail every 15 seconds, and when we set the stop and start times for each trial, we do so here and here to make sure we get the full 3 hours and 20 minutes. Once the trial is complete, the photos are sequenced so we can get an idea of how the snail moved around during the trial. Once we finish a trial, we move our data to a program called Image Pro. In Image Pro, we're able to track the snail's movement by tracking its specific color and size within our area of interest. Once the track has completed, we receive many pieces of data on the snail's movement. We are given total distance, velocity, acceleration, turning angles, and many other useful measurements. You can see the ruler on the side we put for calibration. This helps ensure our measurements like velocity, acceleration, and total distance are accurate. After we receive all our data from Image Pro, we move it into a database in Microsoft Access. Here we can combine data from all our trials and manipulate it in ways we want to answer questions we are interested in. In the database, we can set up queries to tell us things like, let's say, max acceleration for a specific trial. Here we can also compare the data of infected to non-infected snails and see if we can find any differences between the two. And this concludes my first podcast. I'd like to thank you for listening and be sure to be out on the lookout for the next one.